Welcome to Ask and Learn.
Here we want to estimate graphically the critical numbers of the function f of x equal absolute value of 1 plus 5x minus x cubed correct to one decimal place. And here we have the graph of the function on the interval from -6 to 6. As we can see, we have when we take the absolute value, we have this graph where we see this point here, for example, where there is some kind of peak where a function is not differentiable. That's the effect of taking the absolute value. We have also here a number where the derivative does not exist, and here. So there are 3 points where there is an abrupt change in the slopes of the tangents, and therefore these 3 points I mark here are points where the function is not differentiable. That is, where the derivative does not exist, and so, because they are on the domain of the function, they are critical points or critical numbers. We also have points where the derivative is 0, around here, around here. We have a horizontal tangent line at those points. And it seems that there are no more points where that occur because, in fact, this polynomial is of degree 3 and we take its absolute value. So these two lines from here to here goes up without any bound. So there won't be another points where this situation we see here occurs. So these are the only 5 critical numbers of the function, and 3 of them, those marked with the red arrows, corresponds to points where the derivative does not exist, and these 2 here, marked with the blue dots, and now with the blue arrows, are points where the derivative is equal to 0, and so they are also critical numbers. So we did some zoom around those points, each of them, so we are going to see about more or less the values of the x corresponding to those points. So that is the critical numbers, and here we have one. Let's see, let's use red because I use red for those points. So this point here is the first one from left to right where the derivative does not exist. That is corresponds to this point here, and it's a critical number where the derivative does not exist. Does not exist at about x negative 2.1, because we see here the software gave us these decimals, and we can see that the decimal 1 is correct, so we have negative 2.1. So it's our first critical number, negative 2.1. If we do now for the second critical point, but now in this case where the derivative is 0, this one I'm pointing here, so we get this one around here, and as we can see the value is about negative 1.3, or we can say negative 1.2 because we have 1.3 just around here. So I would say that the derivative is 0 at about, that is critical number where derivative is 0 at about x negative 1.2, near negative 1.3, we can say. So now we go for the next one, and the next one, as we saw in the journal graph, is this point here where there is no derivative. And we already see this, so I'm going to the next one, this one here, where the derivative does not exist, and that's about negative 0.1. Very near. In fact, we could say it's negative 0.2 because we haven't arrived to this point. So we have a critical point or number where the derivative does not exist at about x negative 0.2. So we have this other critical number. Now the next one will be this, where the derivative is 0. And let's see, it's this one here. So this is a critical number with derivative of f equal to 0 at about x being 1.3. And we have this, and now we go to the last one, which is another a point where the derivative does not exist, this one here. And we get it, this here, which is the last one, so it's critical number where the derivative of f at x does not exist at about x is 2.3, more or less. So, summing up all the information we saw in the graphs, so we can say that in summary, critical numbers where the first derivative does not exist negative 2.1, negative 0.2, 2.3, and critical numbers where the first derivative of f is 0 are negative 1.2 and 1.3, we can say, and this is very close to negative 1.3, as we said here above, right here. So these are the five critical numbers in total for this function.